So this first bit, we're going to focus on looking at nonlinear relations, and that's what we're looking at specifically as parabolas. But we're going to quickly go through 4.1 and then spend a little more time on 4.2. We're actually going to look at that in two parts. The first part's just going to be some definitions, and then we'll get into actually some of the application stuff. So really quick, investigating nonlinear relations, the idea here is that nonlinear relations don't lie on a line. So if you have an independent variable and a dependent variable, when we put those onto a scatter plot or graph those, what we find is that a line of best fit isn't the best option. So if I take my ruler here and I kind of put this in here, the line of best fit doesn't quite hit a lot of points. I mean, we could put one on there and make it work if we had to, but really this set of points that I have here would best be served by providing a curve of best fit, something maybe like this here, that would better relate to the points than trying to put a line in there. And we can work on these kind of graphs. This is actually kind of a parabolic type of curve, and we're going to talk about that in a minute. So just a quick review, independent variable is our x-axis variable. That's the one that we have control of. So when we're looking at something like a distance time graph, generally we can control how long we're driving, and depending on how long we drive is how far we go, something like that. So then the distance depends on the time that we drive. So that's the dependent variable, the distance, and then the independent variable is the time. Now moving on here into kind of the meat of what we're getting into and what we've been kind of prepping for in the last bit is quadratic relations. And so now quadratic relations, in general, just some definitions here, and then we'll get into some more specific activities with it later. But a quadratic relation in general is something that is modeled by using the equation ax squared plus bx plus c. The important part here is the x squared. It must have an x squared. The b and the c may or may not be there, but there needs to be an x squared in the equation, and that is also the highest power. There's no x cubes, there's no x to the 4s, there's only an x squared, but there has to be some sort of x squared representation in the equation. So the a value can't be 0, because if it was 0, we wouldn't have an x squared. So it can be any real number other than 0. B and c could be any number including 0. If there's 0, then we would just have ax squared, or maybe we have ax plus c, or maybe ax squared plus bx. But we always have to have that a value. The b and c are not necessary. So some quick examples here. We might see an equation like y equals x squared. That's our kind of base quadratic equation. We might see y equals 3x squared plus 4x minus 7. We've seen these before. It's a trinomial. It might come out as a trinomial. Thus, if it's a trinomial, it might also come out as something like this: x plus 2, x minus 6. This is also a quadratic relation, because when we actually expand that out, we're going to get a trinomial. If we expand that out, we would actually get x squared plus, or sorry, that should be a minus. My eraser does not want to erase the plus. X squared minus 4x, and then minus 12. And so there we see that we have, again, that quadratic relation having that x squared there. So any equation that has that x squared value in it and no other power of x, that is going to be our quadratic equation. Now, you can also graph this out. So you'll notice quadratic relation. If you find that when you graph it, it creates a symmetrical. It's important to note symmetrical. That means it's equal if you divide it in half. If you remember the red mirrors back in elementary school, where you'd put that on there and make a symmetrical image, that's what we want to do. We want to actually be able to put a red mirror in the middle of our U-shaped graph, and it should match up on both sides. So this U-shaped curve, which we call a parabola. Okay, this is an important word, parabola. That's a symmetrical U-shaped curve we're working with. So you might see something like this. And if we were to put our red mirror on this dashed line here, that should be equal on either side. You might also see it doing this. Okay, this is also a parabola. And forgive my non-symmetrical drawings, but both of those situations will be a parabola. This here is not a parabola, okay? It's never going to be on its side. It's either going to be facing upwards or downwards. We'll talk about that in a moment. And so another key point on this is the idea of this vertex. And so it's an important area on the graph is when we work with this vertex. So the vertex is the point on the parabola where the graph changes direction. So when we change from going down to going back up, this point right here, or if we go from up and then we turn to down, this point right here where we actually made that change, these points here are the vertex. And in general, the vertex is the points h, k. So our x, y values are known as h and k. Flip the page here. All right. So next is the optimal value. So the optimal value is the y value of that vertex. We often label that part as k, and with, again, the x coordinate being labeled h. So the optimal value is the y value of the vertex. So if I have a little parabola here on a quick little graph, and there's my vertex, this y value here, okay, if that's my x-axis, this y value is our optimal value. Okay, that's our optimal value there. That point in the y-axis is the optimal value. Now we have a maximum value when it's the highest point. Okay, so this is a max value, and in the case where a parabola opens upwards, then this would be the minimum value, and we're going to occasionally be finding those. Another key point, key idea with these is that direction of opening. Does the U open up like a traditional U, or does it open down more like an upside down U, or almost an N without the little line sticking up? So does it open up or down? You can visually see this, or if you look at the x squared value, and actually the a in front of that x squared value, the coefficient there, if the coefficient is positive, it opens up. If it's negative, it opens down. So y equals 3x squared plus 2, that would open up because the coefficient here is positive. Okay, that's a positive number. If we have y equals negative 1/4 x squared plus 3x, in this case here, that's going to open down. Why? Because this value here is a negative value. Okay, so we got a positive value, it opens up, a negative value, it opens down. Now the axis of symmetry is another key point on the graph. The axis of symmetry is the line that cuts the parabola into two equal parts. So this is the line that we'd put our red mirror on to get that symmetrical half. It's a vertical line passing through the vertex. It's y equals h, whatever that h value of the vertex is, that x coordinate of the vertex. So if we have a parabola here, opening up, the axis of symmetry is going to cut that in half through the vertex, and it's going to be labeled y equals h, where h is that value of the vertex. And then the last key kind of definition is a bit of just expanding upon what we know of x-intercepts. So x-intercepts are where the graph crosses the x-axis, as we know from linear relations. Okay, so make sure that it is the x-axis, x-intercepts. There may be one point like a linear relation, but there also might be 2 points, or there could even be no points that cross the x-axis. So it may have 0, 1, or 2 points at the x-axis. They're often called zeros or roots, and so I'll often call them zeros or roots. You won't hear me often use the word x-intercepts. Say find the zeros, find the roots of the equation. You've actually pretty much done all the work that you need to do to get the zeros or roots from an equation that we'll see later. But if we have a grid here, x, y, we could have the graph right here where it doesn't ever touch and thus has no x-intercepts. We could have it down here where it again doesn't touch and there's 0 x-intercepts. We could have it such that it touches and bounces off. So in the case where it comes and just bounces right off the line like both of these graphs, and thus you would have 1 x-intercept, and then finally it could just cross at 2 points either up or down, and in this case we'd have 1 and then 2 zeros. So those are some of the key definitions that you need to know in regards to the quadratic equation and nonlinear relationships as to what we're looking at, and then later on we'll move into actually taking some of this and applying what we've been doing into understanding these a little better.